This is Statistics 243 at UC Berkeley for Monday, October 20th. Okay, let's go ahead and get started. So we're continuing our theme of working with large data sets. I basically have two demos sort of queued up, and we'll see how this goes in terms of actually doing this live. We left off last time where we had read in that airline data set, the 12 gigabytes or so, into one of these FF data sets that was being stored on disk, but we were accessing it from R. So I'm going to do a little bit more with that, and I've already loaded that in. So I did with the ff load command here, and this is on the Radagast server, the SCF server Radagast. But I've also started up a cluster of 12 nodes on Amazon to run Spark in and to do some MapReduce stuff. So assuming I think we should have enough time to get to that, I will then switch over to that. I'm slightly nervous about that because things tend to go wrong when you try and demo things like this, so we'll see what happens. But hopefully it'll be okay. All right, so let's pick up with FF for a little bit. So this data set, once we read in, is something like 123 million lines long, or million observations, and it has 29 fields. And I just loaded it in from this .ff. Basically, it's being loaded in from disk. There's this .ff data file and this .r data file, and the .ff data file has all the data stored, and the .r data is some sort of metadata information. And when you first load it in, what you would actually see is something like I think we saw last time. It'll actually say something like this. So this is a temporary directory on the disk that R creates when it starts up. And so I think somehow what's happening is the information from the .ff data file is somehow then getting put into this temp directory. And it looked like when I was looking at this, it looked like there were 29 different ones of these strings, which I think means that what it's doing is basically storing each of the 29 fields or columns in the data set separately in this representation. And I don't know exactly what the relationship is between these 29 files and the and that .ff data file, but something exists there. Okay, so we've got the data set loaded in, and we can just look at it, and what we'll see is the sorts of things that I just commented in here from the demo code, which is what we'd see is that indeed this is the data set stored here, but it's not exactly in the form of a data frame. So what you see when you print stuff out is some different kinds of information that is indicative of it being one of these special formats. And when we go to do any sort of processing on this, the thing to be aware of is that we're generally going to want to try and use the specific functions and methods that the package provides to be able to work efficiently with this object that's stored in this unusual format. So if we, for example, do get the help information on the FF package, what it will show us, if we scroll down far enough, is there are a whole bunch of functions that are sort of specialized functions having to do with FF that involve the sorts of things that you might want to do with a data frame, like apply and sort and various other kinds of things, order. But there are these special FF functions for doing that. So if you're working with these, it's a good idea to sort of get familiar with what are some of those specialized functions. And there's another set of these functions in the FF base package, which is, as I understand it, sort of statistical add-ons that work with FF. So you can see here in the FF base package, there are a whole bunch of functions that are doing additional sorts of operations. A lot of these don't look particularly statistical. They're basically just sort of processing kinds of functions, but those are all available. So as an example of that, if we wanted to do a tabulation of the counts of the different numbers of flights whose destinations were the various airports in this vector, in this field, in that data set, we could, for example, apply the table.ff function to that, and that should then work with the object, recognizing the fact that it's in this special format. So if we do that, it will go ahead and what it seems like it's doing is basically working its way through these different individual files on disk and getting the information from each of the chunks. Where the chunks, I think, in this case, because it seemed like there were 29 of them, seem like they correspond to the different fields. So I'm guessing now, we'll see if I'm proven wrong, that this is only going to show that it's opening a single one of them, because if they are broken up by fields, this is just an operation on a single one of the fields. Okay, so that might take a little while. Hopefully it won't take too long. So the next thing I was going to ask and see if people had thoughts on this is, usually if we have something where we have a function and then a dot and then the name of a class, what we could usually do is just call the name of the function, and that will do the S3 dispatching to dispatch the class-specific method, which we've already seen a lot of. So the question is, why can't I wish that were a little faster. Question is, why can't I do that in this case? And I will give you a little bit of a hint here. Oh, right. Okay, so if I just look at the table.ff function, we can see that it's a function that does whatever it does. But suppose I look at the table function. Well, that's interesting. Okay, so this is actually contradicting the point I went to make. So I thought, well, let me just explain what I thought was going on, and we'll maybe figure out what is actually going on. When I was playing around with this, what I thought I had to do was put in table.ff instead of table, because when I tried to put in table, it didn't seem to recognize that it was supposed to call the FF-specific version of table on this FF object. And I thought the reason for that was that table was not a generic function. And it was just that if you just look at table, actually I think I'm starting to get a sense of what's going on here. Suppose I look at table here. If I just look at the table in the base package without loading in FF, it's a function, but it's not one of these S3 generic functions. So table.ff, if I call that next, and table is defined in this way, if I call table on an FF object, since this is not a generic function, it's not going to have things set up to then go look for the table.ff function. But what I think I'm now realizing is that once we load in this FF base package, it seems like the original base table function has gotten overwritten by this generic S3 generic. So that I think if FF base as well as FF were loaded in, I think I wouldn't need the .ff here, because I think this table would now be the generic function. I'm curious. Oh, that's in there too. Yeah, so now I'm not sure why I got confused when I was setting this up. All right, well, that may or may not have been helpful. Maybe that delayed enough time for this to finish. So if we look and see what's the class of dest table. So this is now just an R array. So it's gone in, it's done a bunch of processing recognizing the FF format, but it's returned the results in a more standard format to us. And we could go ahead and look and see what this thing looks like. And it looks like it's been sorted. It's basically saying how many, I forget whether, so this was how many arrivals there were at the different airports. This makes sense. This is Chicago O'Hare, this is Atlanta's airport, this is Dallas Fort Worth. These are the big airports in the United States. So that seems to at least validate that we've gotten something reasonable back. All right, let me just pause and say, are there any questions about sort of anything that I've done so far or what I'm trying to illustrate here? And you can still do things like, just looking at individual pieces of the data set. Here's another example of where I'm calling the min, one of the FF specific functions explicitly instead of just calling min. Again, trying to make sure that I'm using the one that recognizes the format of the data set. Because the danger, as I see it, is suppose it just tries to use the standard min function on this object. It might work, but what it might be doing then is basically coercing this into a standard object, a standard vector or data frame, and then it's presumably going to potentially use up a lot of memory and potentially not work as efficiently if it does that coercion. So I'm trying to make sure that it is doing the FF specific one. So I guess this is a better illustration of the fact that it's a good idea to call min.ff instead of just min, because min is not actually defined as one of these S3 generics. Min is just defined as a standard function. So if I call min here, it's not going to go and dispatch and call min.ff because this doesn't have the dispatching mechanism set up. Okay, I think I may not bother to run that just because it might take a little bit of time. Okay, and then the other thing I want to make the point about here is that in a lot of these cases, once we're working with these sort of higher level packages and functions that are particularly doing things with really big objects, that oftentimes if you say object A gets or is assigned to be object B, or object A equals object B, what's not going to happen is you're not going to get a completely new copy of the object made and now have two different copies of that object. What you're going to have happen is what's called a shallow copy made, which is basically a pointer copy. So instead of having two separate distinct data sets, you're going to have one distinct data set and two names pointing into that. And even if you change an element of that data set using one of the names, that would be then reflected in the data set pointed to by the other name, that they'll just still be pointing to the same object. So being aware of this idea that in a lot of these kinds of contexts, unlike in standard R where sometimes there's the delayed copying, but once a change is made to an object, you would have two distinct objects. Then in a lot of cases here, you're just going to get basically two pointers, two names pointing into the same object. And if you really did, in this case, want to make a copy of it, you can use this function called clone, which would make what I'm calling here a deep copy as opposed to a shallow copy. Okay. Let's see. Oh yeah. So this did confirm that it did indeed only open one of those files. So that's a bit more evidence that indeed it's breaking things up into separate files, one for each of the fields. Okay. So then the next thing I wanted to do was look a little bit at running statistical models on these things. And again, I think just because it would take too long to actually run in real time, I think I'm just going to show you the results of doing this. So what I'm doing in terms of fitting this is I'm using this big LM package, which is designed to fit these very large models and work efficiently in terms of not using too much memory and being able to use these special data sets that are these file-backed data sets that are not sitting all in memory. Okay, so what I'm going to do here is I'm going to load that in, and then I just did a subset where I said, okay, this is going to be not one of the world's greatest, most justified regression models, but just for the sake of illustration, I'm saying, okay, get rid of the elements of the data set where the departure delay is, or include only the ones where the departure delay is less than 12 hours and larger than minus 30 minutes. Under the supposition that if the delay is less than minus 30 minutes, something weird is going on in the data set, flight leaving more than 30 minutes early, and that we might not want to, there might be some issues with outliers, so I'm going to fit a regression just for the simplistic, this is not what we would usually do in a regression context, but just for simplicity here, I'm going to exclude any of the very large values in the right tail of this empirical distribution of the delays. And then I'm also eliminating any of the missing values. And then I go ahead and I fit this big GLM, and the call looks pretty similar to fitting a standard LM or other kind of GLM. I can give it day of week, and I think I've read this in such that this is a factor variable. So this is going to get interpreted as the different levels, one level for each of the days of the week, with one of the levels not being included because it would it would not be identifiable relative to the intercept. And then I also have distance in here. And so you can see when I go ahead and fit this, this is the data set that is something like 12 gigabytes. I can fit this model. I wouldn't be able to fit it unless I had a huge amount of memory if I weren't doing it using this FF package and the big LM package. And it takes something like 7 or 8 minutes to run in this case. And then the results I get back, which are unfortunately split across the page, are this is the average delay in minutes, is the intercept adjusting for the other variables. This is the effect of 1 kilometer greater the distance between the airport where just the distance that the flight is from the departure to the arrival airport. In some of the other stuff I've done, I've rescaled things to be in thousands of kilometers because that's going to be a better strategy numerically to avoid potential numerical issues of ending up with very large numbers. Because these things often get squared in doing the regression calculations. And then these are the day-of-week effects. So the baseline category is Monday, so this is saying, okay, there are fewer delays on Tuesday, somewhat fewer on Wednesday relative to Monday, more on Thursday, many more on Friday, many fewer on Saturday, and somewhat more on Sunday. And this sort of fits, if you've flown in the United States at least, that's sort of a standard pattern for delays, that at the end of the week, delays are often worse. So at least, again, sort of it fits with our intuition. So this is really just an illustration that you can do these things and actually can fit some of these models with fairly large data sets, still just working within R. Any questions or comments?
Is it better to remove missing values before doing the regression? Like, will it run faster? It'll just remove them anyways.
Yeah, if we're just doing this in LM, it wouldn't really matter, although it's good to be aware that LM is just going to be throwing out missing values, because oftentimes that'll happen behind the scenes and you won't be aware of it. So it's good to sort of know that's happening even with LM. Once we're working with these very big data sets, it's often a good idea to do things more explicitly ourselves. Like we saw that when I think I mentioned that it's a good idea to explicitly specify what are the types of the columns when we read in the data set. And similarly, I think sort of an analogous situation here is that it's probably a good idea to explicitly exclude the missing values. It might work if you didn't, but oftentimes it's good to be careful about that and do it manually yourself, just to make sure things are running the way you behave and running the way you expect and that they're behaving properly. For some of these things where the package really is sort of built in, where this is an R package and it's sort of designed to work in the way that other standard R functions work, it might actually work fine without us removing the NAs. But with these big data sets, it's often a good idea to do it ourselves. Okay, any other questions? So the other point I wanted to make, and I'll just do it by illustration here, is I already mentioned a couple of caveats about thinking about these really large data sets, that even though we have a big data set, correlation is still not causation, and particularly because we have a large data set that might be collected in some very haphazard manner, that it's probably not going to be a representative sample of any particular population that you might be interested in. The other point I want to make here is just about the fact that when you've got a big enough data set, you're going to see statistical significance in almost every variable that you look at. And that's not going to be a very good screening tool for trying to understand what are the important things going on in your data. So I'm going to do this by illustration by I'm just basically generating data under this particular model. So I have a single x, there's a coefficient of 0.01 and an error variance or error standard deviation of 1. And I'm going to generate not just for one x, but for 3 x's. So I'm going to assume that there are 2 x's that have an actual 0 relationship with the outcome. Yeah, Kelly?
So maybe this is my lack of statistical knowledge. What's the significance of having 0 plus the coefficient times x?
Oh, nothing. That was just me illustrating that the intercept is 0. So this is the true model that I'm using to generate the data. The intercept is 0. The coefficient on the first x, the notation here is not great. For coefficient on the first x is 0.001. I'm going to have an x2 and an x3 where the coefficients are 0, which I should have just put in there if I was being explicit about it, so I'm sort of mixing and matching here. And so here's how I generate my data. I generate x1, x2, and x3 from just random uniforms. I generate y as being this relationship. It's a linear relationship with x1, but no dependence on x2 or x3. And here what I'm doing is I'm just generating this big simulated data set in chunks. I'm writing it to disk, and then I'm going to read it back in using the FF package. So I generate it in chunks because some of these chunks, because I'm trying to create a big data set. Okay, so I read it back in from this file that contains the simulated data. The file is called signif.csv. I have to read it back in. I do the business with getting it into the FF format, and then just if I want to redo it, I save it back out, and then I load it back in, and then I fit the regression model. So this is the model I'm fitting. I don't know that x2 and x3 are not related to the outcome, so I'm including. I'm pretending I don't know, so I'm including them in the regression as regressing y on x1, x2, and x3. And now I'm going to look at the results that I get, and I'm going to calculate an r squared here. So this is just sort of manual calculation of the r squared, and here's what I get. So this is my result. I get that the estimate of the intercept is pretty close to 0. I get that the estimate for x1, where the true regression coefficient is 0.001, so I'm not too far off. And what do we see? We see that I get a 95% confidence interval, a pretty small standard error relative to the size of the coefficient, and a very, very, very significant predictor in this model. And for x2 and x3, it actually works out. x2 and x3 really aren't related to the outcome, and I get coefficients that have p-values that are much larger than 0.05. Okay, so in some sense, I guess this sort of validates doing classical statistics and looking at p-values. On the other hand, if we look back at that model, the magnitude of the true coefficient of 0.001 is really small relative to the error variance. And if I actually calculate the r squared, in this case I calculated the r squared just for the first 1 million of the observations, and I actually got that the r squared was negative. Okay, so less than 0. If I calculated this r squared across the whole data set, it wouldn't have been 0, but it would have been very, very, very small. I don't know exactly how small. So the point I'm making here is just that in basically any of these kinds of regressions you run, you're going to get a whole slew of significant predictors, and in most cases that's not going to be particularly interesting or important to you because it's not going to indicate that they're important in any substantive kind of sense. It just means that you can say with a fair amount of confidence that the intercept that the coefficient is not 0, but that doesn't mean it's big enough to be interesting. So I have this point, I have this comment about, if I'm a physicist and I'm looking for the Higgs boson, and maybe then in that case that might be a case where finding very, very small effects that are significantly different than 0 is something I'm interested in. But in most practical applications, this wouldn't be particularly interesting. Chris?
Can you do penalized regression, like a lasso that would reduce the coefficient?
Yeah, there's tons of other things that I could do in lots of these cases.
In the big FF.
Oh, you're saying specifically here? I suspect not. I suspect we'd have to code it up ourselves. So maybe sort of a two-part answer. One is there are lots of things, if this were sort of a pure statistics class where we're thinking about modeling, where we could think about what are the actual sorts of models that we would want to fit that would sort of address some of these kinds of issues. Since it's not, I'm not going to go into them. And then also sort of Chris's point that in a lot of the cases, the sort of technology hasn't really caught up here. So we can do a lot of we can do some of these basic models, but if we wanted to do any more sort of sophisticated models, that's something that we might not be able to do without writing our own code. All right, so can anybody tell me why the r squared is negative here? An r squared in a data set with training data should never be negative, right?
Numbers that are squared should unless they lie.
Yeah, I mean, it's not actually calculated by squaring anything in this case. It's the 1 minus sum squared error over total sum of squares. So think about what's going on here pictorially. We've got a regression. So let's see. So this was 0. The true slope is whatever 0.001 is on whatever scale I have on my y-axis here, right? And I've got a ton of points, right? So I've got a ton of points around this true regression line. But in this case, I didn't bother to do the calculation on all of the observations that went into it. I only did the calculation on some subset of these observations. So any thoughts about why I could get an r squared of less than 0? What does it mean if I get an r squared that's less than 0? What does it mean about the fitted line compared to having having a slope of 0? Zhuang, any ideas?
When you calculate this R squared, did you use the population sample variance minus the
Yeah, I basically did it.
the variance of the random noise?
Yeah, I did it right. I did it as 1 minus, and then I have this ratio here.
Yeah,
This is the total variance on the bottom, and this is the residual variance.
So you only use part of the data, so the variance may be not. The variance may be smaller or big than 1. Right? But
Yeah, I mean, so I guess right. So there's nothing that says this ratio has to be less than 1 if I'm doing it on a subset of the data. Like so one way to think about it is just because this regression line is better than the flat line on the full data set doesn't mean if I restrict this to some subset of the observations that this line is a better fit than just fitting the mean to all of the observations. Okay, and in general this is the sort of thing that might happen if you've got this case where the fitted line is very, very similar to just having a flat line and just explaining everything with the mean of the observations. So for this subset, explaining all the observations with their mean is better than explaining it with the line that was fitted to the full set of observations. Of course, if I had done this for the full set of observations, I would have gotten an R squared that was a little tiny bit bigger than 0, but it probably would have been something like 0.001 or something like that, or 0.0001. I didn't actually calculate it. Okay, so any other questions or comments?
Does it matter the variance of x? So here the coefficient compared to variance is very small. So suppose we have a very, very small variance.
Yeah, I mean it's always going to be the usual case in a regression of how much is the total variation, how much is the variation explained by the model, or 1 minus the variation in the residuals divided by the total variation in the observations. And that total variation in the observations is going to depend on what the slope is and how widely spread the x's are and how big the residual variance is. So all that's going to play into it. Okay, so let's see. I had a little bit of a comment here about sparsity, which is that one standard technique for dealing with big data sets is if you have any sparsity in the matrices that you're working with, to make sure you take advantage of that computationally, because we shouldn't be doing any calculations with zeros that we don't need to, because we know that any multiplication with a 0 or addition with a 0 is not going to change the result, or you know what I mean. So there are lots of cases in terms of statistical methods that I'll leave you to read on your own, where we do end up oftentimes with sparse matrices, and there is a lot of functionality in lots of languages, including in R, for representing things as sparse matrices. Here's an example using this package called SPAM, which stands for sparse matrix. I'm creating a matrix, and then I'm converting it to one of these sparse matrices, and I've set a lot of the elements of the matrix to 0. And what you see is that the size of the sparse matrix representation relative to the matrix representation, the original matrix representation, is much, much smaller. It's 26 megabytes compared to 800 megabytes. And I can also see that if I go ahead and take the matrix and multiply it by a vector, versus taking the sparse matrix and multiplying it by a vector, that there's a 40, in this case, there's a 40-fold magnitude difference in the amount of time it takes to do that computation. Yeah, Eugene?
Is this the way the SPAM is implemented, or is this because of the actual sparsity? Like, is there an underlying C code which is not there for regular matrix?
No, because this goes directly to C code calling the basic linear algebra subroutines. And so it's not that this is coded inefficiently. This is coded actually quite efficiently. It's that you're exploiting the sparsity in the algorithms that are used for doing this with a sparse matrix.
So implementation is wrapped around class sparsity?
I haven't looked. I think SPAM sort of codes up some of its own functions for doing some of the linear algebra. Yeah. Okay, so that was just a very brief note about sparsity. The other brief note I have here is if you're dealing with big data sets, there are lots of things that we can do that basically make use of statistical or probabilistic tools to improve the computational efficiency. So oftentimes we could just take a sample and do the analysis on the subsample, a representative sample of the data set, and we're probably going to get a very similar answer to if we use the entire sample. There are some other ideas sort of similar to that in terms of randomized algorithms that basically take random samples of the data set, and if it's an iterative algorithm, they might take a different random sample of the data set at the different iterations. So lots and lots of ideas around these sorts of things that people have been thinking about over the last 5 or 10 years, including a lot of pretty clever work going on here at Berkeley. So I'll just leave that as just sort of a comment that those exist, and now let me skip over to MapReduce. So part of what my goal for the first sections of this unit was to say that even if you have a big data set, doing things with Hadoop and MapReduce is sort of trendy these days, but that doesn't necessarily mean it's going to be the most effective thing for you to do on any given problem you have. And so we've talked about a lot of techniques you can use that involve a single machine oftentimes, and just making sure you're doing things in an effective way in light of the memory and computational constraints you have. That being said, it's useful, I think, to know about MapReduce and some of the tools that use the MapReduce framework. And so we're gonna spend the rest of today, and then actually, given the time, probably most of Wednesday, going through an example here. Okay, so originally this idea of doing MapReduce came out of Google, I don't know, 10 or 15 years ago, and the idea was they had these huge data sets, and they needed basically a paradigm that instead of everybody going in and writing their own code that says, okay, take this huge data set, split it up onto lots of machines, and then write your own code to go and pull the information from that machine that you need, and pull the information from that machine that you need, and pull this information, do something with it, then you maybe need to sort of write results back out to all those machines, and maybe you need to do a lot of management involved here. And what happens if you're using 1,000 machines and one of those machines happens to go down in the process of doing that? And then you have to be like, oh, that machine went down, 1/1000th of my data set is stored in that machine, I have to go take it and move it to a different machine and rerun the processing and all this. So basically my understanding of this is that the whole sort of Hadoop infrastructure and the idea of doing algorithms that fall in this MapReduce paradigm came out of this idea of sort of, MapReduce is not really an algorithm, it's sort of a meta-algorithm. Like if you can take your algorithm and express it in the MapReduce way, then you can use these tools. And so the idea was to create this meta-algorithm and then have software that would basically implement this meta-algorithm in a robust way across many, many different machines. And it's sort of a counterpart to this message passing kind of thing, which is this sort of traditional high-performance computing thing that has in the last 20 or 30 years been going on these supercomputers. So there's sort of two distinct kinds of parallelization across multiple nodes. Okay, so that's sort of the very, very big picture. So the basic idea so Hadoop and Spark, which is what we're going to concentrate on, are basically software tools that allow you to implement this idea of doing MapReduce. And what MapReduce basically is the idea is you're going to take your huge data set, you're going to split up the data set on disk across the disk drives of many, many different machines. And then you're going to code up any given algorithm that you want to run in a way that works with the fact that the data set is split up in these different chunks. And so inherently, this paradigm is basically working in the context where you basically have many, many, many independent observations, and that you can do calculations where you basically go in and apply some function to each of your observations separately. That will do some transformation on your data set. And then in some cases, what you're going to want to do then is basically collect some aggregated result back from all of those distributed chunks of your data set. So it often falls in this sort of two-stage process of you have one or more map steps where you take your original data set, you apply some function to each of the observations to do some transformations, and then you have some reduction step where you're basically taking some summary statistic of all those observations and collecting that summary statistic back on the master node. So if you can sort of write an algorithm such that it fits into that way, then you can use these tools for your algorithm. And this could be iterative. You could go out, you could do a map or multiple map steps of transformations. You could then collect the results back as summary statistics, and then you could send those summary statistics back out to all the worker tasks and do some additional map steps and do it in this sort of iterative fashion. We'll see an example of that when we're fitting some data in a little bit. Okay, so before I say a little bit more specifically, any questions about the big picture of what I'm talking about here? Okay, so sort of the traditional way of expressing MapReduce is often to do it in terms of, to frame it in terms of these things called key value pairs. So this is basically that every single value or observation in the data set would also have a key, which would basically be a name. And in some cases, the different values multiple values would share the same key, so there'd be some sort of natural grouping or stratification to the data set. And so in that case, the way you can think about the MapReduce paradigm is I'm going to read in my individual data, and a common case would be these would just be individual lines from a whole big collection of CSV files or something like that. And then what I would do is with each of these lines, I'm going to basically create these key value pairs. And so the mapping step would sort of, if you could think of the individual data objects as being the key, that the initial data set is basically, I have a whole bunch of files and the key is the name of the file, then the first mapping step that I need to do is basically work my way through those keys, through the different files, and basically do sort of a mapping where I go from however many files I have to a data set that's a collection of observations, sort of aggregate, taking all of the lines from every file. And so the new set of key value pairs would basically be an identifier for each line and then the value that was stored in that line. And then a reduction step would be, well, let's make another example here. Suppose what I then did was that I created a set of key value pairs where the keys were, say, the destination airports in my airline data set. So now I have a set of key value pairs where every observation is associated with a key, and the key if it identifies the grouping by airports. So now a reduction step might be to go in and say, okay, for each one of those keys, take the mean of the delays for all of the flights that are associated with that airport. And so that would give me back the summary statistic, which would be the stratified mean delay by airport. Okay, and so I might collect the result of doing that reduction step back at the master process, and then that would be my query, and you could think of that as being a very basic analysis. I just want to see how does the mean departure delay vary by different airports, and which ones are the worst ones and which ones are the best ones. Okay, so it's not a particularly interesting analysis, but it is an analysis that sort of fits within this paradigm of doing these operations of map and reduce operations, and of thinking about these key value pairs and potentially grouping by keys. Okay, so basically Hadoop is an infrastructure for enabling this sort of operation, and for sort of managing the fact that you've got multiple nodes that are doing these calculations and keeping track of the fact that you've got your data set distributed across multiple nodes. And there are some R front ends for working with Hadoop. There are packages called R-Hadoop, and I think this is called Repe. You probably don't want to pronounce it R-Hype. Okay, so that's sort of the backdrop. So what is Spark? So Spark is sort of a new Hadoop-like implementation that came out of the AMP lab here in EECS at Berkeley. And the basic idea of Spark is that in some cases, if you have a big enough cluster, you might actually be able to fit your entire data set into memory if the memory that you're thinking about is the collective memory across all of the nodes in your cluster. So if that's the case, as we've been talking about in other contexts, it's often going to be faster. It's usually faster if you can do calculations in memory than if you have to be writing to disk and reading from disk as part of your algorithm. So the idea of Spark was, when it's possible, try and keep the entire data set in memory, in the chunks of memory across the different nodes, and when you need to do, say, an iterative algorithm, if you've got the data set already sitting in memory in this distributed fashion, you could say, you could make an instruction that says, go out to each of the nodes, do some processing in memory, and produce another data set basically sitting in memory, or a transformation of your data set that would still be sitting in memory. And you could even write sort of iterative algorithms that would have multiple steps involved, and they're going to be more efficient if everything is able to be kept in memory. So that's the basic idea. In some cases, of course, you might have a data set that's just not going to fit in memory on the given nodes that you have available to you, and in that case, Spark will automatically put stuff to disk when it needs to. Okay, so let's see one more sort of basic example, and then we'll actually turn and actually use Spark to try some stuff out. So this is sort of the hello world for Hadoop type stuff, and it's basically just suppose I have a huge number of documents and I want to count up the number of times each word occurs in the document. Okay? So the way that you could write this is write a map function that takes in the name of the document and then takes in the all the words in the document. And what would the map function look like? Again, this is just sort of pseudocode. It would say, okay, for every word W that's in this list of words document, the list of words that's stored in this object document, I'm going to return back W. This would be the key, that's the word, and then I'm going to return back the value 1. And that would be the value associated. This is the key value pair. Okay. So if I do this operation, this mapping operation on all of my documents, what I'm going to produce is a new transformed data set that is basically for every time a word occurs, it's going to be that word and then a 1, and that word and then a 1, and that word and then a 1. And so the word the is going to appear a ton of times. It's going to be the 1, the 1, the 1, and then Andrew 1, Andrew 1, Andrew 1, etc., etc. So that's the new transformed version of the data set. And that's the result of doing this map operation. And then the reduce operation says, okay, the reduce operation is going to have to basically work on some sort of object that is basically is called an iterator, and that basically has, in some sense, is storing up all the information associated with a given key, although it's not really sort of storing it all as part of one object. But basically, in this particular way of writing it, this says, okay, the key is going to be the word, and then the values are going to be stored in this iteratable object that I can work my way through. And then what does the reduce function look like? Well, it's basically a function that is going to work its way through the different elements that are associated with a given key, and it's going to have a running sum where it's just going to add up these values. And remember, these are just 1 at every time, so this is just counting up the number of times the word occurs. And then it's going to return back the same key, and instead of having a whole bunch of 1s, it's now going to have the sum, the value of the sum. So that's, in this case, what the reduction looks like. And here's, I don't think I'll say too much about this. This is actually, I think, real code from this RMR package, which is part, I think, of the R Hadoop package, of how you would do a basic little map reduce kind of operation with some R code. So I'll let you guys look at that on your own. Okay, so finally let's look at doing this actually in Spark on an Amazon cluster. So part of the goal of this and of the next homework is basically having you guys just get a chance to play around with and be exposed to some cloud computing and to doing this stuff in a distributed fashion. So what I've got here is I'm on the VM, and I sort of already ran a bunch of this because otherwise it would just take too long. But here's basically what I'm doing on the VM, and I'm going to ask you guys to do very similar stuff for the problem set. So I've downloaded, I would make this bigger, but I keep forgetting how to make, in the VM, how to make it bigger, so I apologize for that. I've basically downloaded the Spark software onto the VM, and it's sitting in a directory Spark / something else. And oh, this is not totally right for the VM. This is if I was doing it on the SCF. But I basically have to set up some credentials for this to work. So I basically need to set up some password kinds of information for Amazon to be able to connect up to to be able to create an Amazon virtual machine or set of virtual machines. And then I also have to set up SSH keys so that I can log into my virtual cluster without having to give a password, because that's how Amazon sets it up. So for any of you, so this is basically just using these things called RSA keys, where I have the private version of the key and Amazon has the public version of the key, and then as long as I'm using the right key pair, that will allow me to log in via SSH without using a password. So these guys are the things that allow me to start up an Amazon instance. And as long as these are set, then I'm going to run this script that's provided by Spark, that is the special Spark script for starting up a virtual cluster of nodes on Amazon. So I'm going to run that script, I'm going to tell it what the name of my key pair is. This is for the SSHing. And I'm going to point to the private version of my key, which is often stored in your home directory in .ssh. That's a good place to put it. I'm going to say start up the Amazon cluster in one of the particular regions where Amazon has its computers. And then I'm going to set the fact that I want to start up a Spark cluster that will have 12 slave or worker nodes and 1 master node. So that's the S flag here. And I have to tell it the version. This is sort of a flag that says when you're starting up, wait at least 5 minutes for the nodes to start up before you try and access them. That's important, otherwise some things will sometimes fail. And then I'm going to launch the virtual cluster. So I've already done that here. This is already launched. And if we went back up to the top, when I was starting to launch it, there's sort of too much that went past the screen. I can't actually get all the way back to the top. But this is the sort of stuff it will print out. It will say, okay, I'm doing all this management to basically install the Spark software on all of the nodes of the cluster and to start up all of that software in a way that it can be used. And so you'll see a whole bunch of stuff where it's basically giving us startup information and saying what it's doing and talking about installing software. And eventually, after 5 or 10 minutes of doing that, it will return back. When you guys do this, you don't need to worry about this failed message. It seems like that seems to be fine and not cause a problem. Eventually, it'll say, okay, I've started one of these this Spark cluster. This is the IP address that would allow me access to it. And then it says done, and then it returns me back. This is back to the VM prompt. Okay. And then what I did was I said, okay, good, my cluster started up. Now what do I need to do? Now I need to basically SSH in. And I could just use SSH. As long as I say SSH minus I and then give it the private key for the SSH key pair, and then if I were to SSH to this address here, between here and here, that would allow me to just SSH in as if this were any remote machine. It happens to be a virtual machine, but I can SSH into it. The Spark scripts that allow you to do a lot of this also provide a sort of login functionality, and so we can also log in by calling the Spark script, again giving it the key, telling it what region, and then just say login Spark. I guess that went off the screen and it's not appearing over here for some reason. Log into the Spark VM, and so once I do that, it turns out I had an error in the file that I was pointing to. Once I do that here, then what does it do? It says, okay, I'm searching for a cluster. I found a master in the 12 slaves. This is the URL for the master. That's what I'm logging into. And then it's going to return back at some point here and say, hey, your root on this machine, and this is an internal IP address as opposed to a world viewable IP address. This is just internal to this set of nodes, or maybe I guess it's internal to Amazon. And so now you're basically sitting at the command line of the Linux command line of the master node of this cluster. So that's what's going on there. And so at this point, the next thing that I want to do is I want to get my data onto the distributed file system. So this is called an HDFS, a Hadoop distributed file system. And basically what I need to do is I need to take the 22 files that have all of the airline data on them. I need to get them from my SCF account onto the virtual Linux machine, and then I need to take them from the virtual Linux machine and get them into the HDFS, the distributed file system of those 12 slave nodes, so that I can then do a bunch of processing on them. So that's sort of what I'm doing here. I'm setting up some paths because the Hadoop command here is located in this particular directory of the file system of the virtual machine. And so then what do? I say make a directory called /data, except I'm not doing this on the Linux machine. I'm doing this in the Hadoop file system, which is distributed across the 12 slave nodes. So I have to call Hadoop and then Hadoop FS, and then I give it a Linux-like instruction, make directory, but it has to have this Hadoop FS minus in front of it. So that says make this /data directory, and then I say within that make a /data/airline directory. And then I say copy all the files from my Berkeley account over to locally to /mount/airline on the Linux machine. And then finally, once, and I'm just going to do 3 of them instead of all 22 for the sake of time. And then finally, I'm going to copy them from the master node, master Linux machine. I'm going to copy them onto this into this HDFS directory. And then they're going to be sitting on the HDFS directory available to us to do processing on them. So when we pick up next time, we'll actually start working with those files and doing these distributed processing calculations using Spark.
Is there any particular reason you want us to use Amazon Web Services or are we free to use like Google Compute Engine or like other managers?
Yeah, we're just using Amazon because it's sort of what Spark is set up for in terms of setting up these clusters. You know, if we wanted to do all systems administration, we could do this on Google or anywhere else.
But if I wanted to use something else, it would be okay to use something else as long as I have.
Yeah, I guess you mean for the problem set?
Yeah. So do I have to use
I guess you don't. You don't have to, but we have. If you do something else, you can pay for it. We have credits. Yeah, if you, I guess if you don't, it doesn't matter.
Okay.
But you would need to get Spark installed.
Yeah, my husband's the manager that I can start to use. Yeah, because he actually.
Yeah, we have some credits for this.
Okay.
But if you want to play around with it, it'd be curious to see how it differs.
When will the project start? At the end of the
Sort
month?
of mid-November,
Oh,
probably.
mid-November, okay.
Yeah.
And
I got your problem set there.
yeah, I got it. Thanks.
Yep.
And we'll have homework during the project?
Yeah.
Okay, so we'll still have like assignments.
Yeah, but the last assignment will probably be due the last week of class.
Okay. Very well. Thanks.
Yep.